This is a new chapter, that is electromagnetic induction, or simply EMI, electromagnetic induction. Well, student, in the magnetic effect of electric current, in the last section, in the last chapter, we have discussed that when a current carrying conductor or when a current flows in a conductor, it produces the magnetic field around it. Means the magnetic effect of electric current is known to us. So far it is known to us. But the reverse thing is that, can we produce the magnetic effect, or can we produce the current, or can you develop the current by a magnetic field? By a magnetic field. The reverse. In the magnetic effect of electric current, current produces magnetic field. Here we will discuss, can we produce, or how can we produce the current due to a magnetic field. So, in this discussion of electromagnetic induction, so this means this is a combination of two things, one is the electric and magnetic. So this is the electromagnetic induction, means induction of or inducing the electric current or electromotive force, EMF, inducing EMF. The EMF gives you current. The EMF gives you current. That is known to us. So the method of, or the phenomenon in which we can induce the EMF, or in a closed circuit the EMF gives you electric current, induced current. That current is called induced current because of a change in magnetic field, or change in magnetic field, or that you can say that magnetic flux. The magnetic field for area, that is called as the magnetic flux. The magnetic field into the area, that will give you the magnetic flux. So by changing the magnetic flux, we can induce electric current, or the current comes because of induced EMF. That is called as your electromagnetic induction. And this was first observed by Faraday and Henry. This was first experimentally observed by Faraday and Henry. We will discuss about the Faraday experiment. Then from that Faraday experiment, what is the conclusion he got that, and what is the law he gave, that is called as the Faraday's law in electromagnetic induction. That also we will discuss. Okay. So first I can say that what is this electromagnetic induction means? It's the phenomenon of producing the phenomenon of producing induced EMF. The phenomenon of producing induced EMF, and hence induced current. That EMF gives you current. Because of EMF you can get a current. So the phenomenon of producing induced EMF and hence induced current. And the current comes, the EMF is there, the current comes in a closed circuit. So I can write this also. And hence induced current in a closed circuit. In a closed circuit due to the change in magnetic field. Due to the change in magnetic field, or change in magnetic field, or that is the change in magnetic field in an area. If the magnetic field change in area, or magnetic field lines, magnetic field is represented by magnetic field lines in an area that multiplied gives you magnetic flux. So by changing due to the change in magnetic field, or that you can say that by changing the magnetic field or change in magnetic flux, or due to the change in magnetic field or magnetic flux, change in magnetic field or magnetic flux. Okay? Link with the closed circuit. Link with the closed circuit. With the closed circuit. What the magnetic field or magnetic field flux link with the closed circuit is called, or is known as electromagnetic induction, or you can say it's known as EMI. Clear? The phenomenon of producing induced EMF and hence induced current in a closed circuit due to the change in magnetic field or flux linked with the closed circuit is known as EMI. The change in magnetic field or the change in magnetic flux linked with the closed circuit is known as electromagnetic induction. And this was first observed experimentally by Faraday and Henry. So that is also called as Faraday's and Henry's experiment. Clear? And before I go to this topic, already you know about the magnetic flux, that I will not discuss here. That is also required here, because there is a change in magnetic flux gives you induced EMF. That method is a change in magnetic flux induced EMF. You have an idea about induced EMF. If that is the coil is in a closed circuit, so a EMF is induced in this coil. A EMF is induced in this coil. If it is in a closed circuit, if I close that, then that will give you induced current. Why it is induced? Because it is induced because of the change in magnetic flux. There is no EMF. It is induced. So that's why it is induced EMF or induced current. Because of change in magnetic flux. And already you know about the flux. So what is that magnetic flux? Let me again repeat. Recall that magnetic flux phi B, or simply phi is equal to in this case, or M is equal to phi, and magnetic flux equal to surface integral of B magnetic field dot ds. B dot ds. That already you know that. Number of lines of force in a area, in a cross-sectional area, that will give you the magnetic flux. Clear? That already you know that. Okay? Or B phi is equal to small magnetic flux equal to, you can say B dot ds. That already you know that. I will not discuss all these things. Now we will switch over to the next thing, is that Faraday's experiment. Okay? So now I will go to the Faraday's experiment. Okay, now comes to the Faraday's experiment. So what that Faraday's experiment? The observation is that suppose there is a coil. How it is done the experiment? So there is coil. It may have number of turns, and into the coil a galvanometer is connected. So this is a galvanometer is connected to the coil. There is a closed loop or a coil connected to a galvanometer. As shown like this. This is a galvanometer. Let this is a galvanometer, and like this. And this is a coil. First, what we observe? A coil of a conducting wire is connected to a galvanometer, and a bar magnet like this. There are two poles, north pole and a south pole. They are placed like this. When both the coil and the bar magnet are at rest, both the bar magnet and the coil are at rest, there is no deflection in the galvanometer. Clear? First observation is what? There is no motion between these two. There is no relative motion between the coil and the bar magnet, means there is no deflection in the galvanometer. First observation. Next. Then what was done? Let the north pole of the bar magnet points towards the coil. The north pole of the bar magnet is towards the coil and moves towards the coil. The north pole of the bar magnet moves towards the coil. The north pole of the bar magnet moves towards the coil. North pole of the bar magnet facing towards the coil and moves towards the coil. Means there is a relative motion between the coil and the magnet. Then it was found that, or he found that, there is a current flows in the coil and the galvanometer shows deflection. If a current is there, the galvanometer shows deflection. So it gives a current flowing in the coil like this. There is a current flows in the coil like this. We will know that in what direction the current will flow. So he found that the north pole of the bar magnet, when points toward the coil and moves toward the coil, the current flows in the coil. One observation. Next observation. Second. Saying if the bar magnet moves away from the coil, then the galvanometer shows deflection, means there is a current, but the deflection is opposite to the previous one. Here, if this is the deflection, in the second case, when the north pole moves away, the deflection is opposite. It shows the current is in opposite direction. The current is in the opposite direction. Clear about this observation? Clear? When both are at rest, there is no deflection in the galvanometer, shows there is no current in the coil. But when the bar magnet with its north pole facing towards the coil moves towards the coil or away from the coil, the galvanometer shows deflection, but they are in a opposite direction. This is also same for us. By facing the south pole also, by facing the south pole toward the coil and moves toward the coil or away from the coil, it shows the deflection, but the deflection is opposite to the what happens when the north pole is moving towards or away from the coil. Means when the two coils are moving toward the coil or away from the coil, it shows deflection. Is that clear about the observation? Next. The same thing is that by keeping the rest, suppose the bar magnet is at rest and the coil is moving towards the bar magnet or away from the bar magnet. Taking the coil moving towards the bar magnet or away from the bar magnet. The same thing is happening. The current or the galvanometer shows deflection, then it gives a current. And this current is called induced current. This induced current comes because of induced EMF. Clear? Now the question is, why this happens? When the bar magnet moving toward the coil or away from the coil, it shows a deflection. And the deflection is the opposite direction, that we will know later. But it shows a deflection. Why? The galvanometer shows a deflection, means a current exists. Because when the bar magnet, suppose the first case, suppose you take, let me explain this thing, what happens here, north pole and the south pole. So if it is a bar magnet, so it will produce a magnetic field. Like this, suppose this is a north pole, so the lines, magnetic field lines are coming from the north pole, some are entering toward the south pole, like that. These are the what? Magnetic field lines. And from the south pole is like this, coming toward the south pole. So these are the magnetic field lines. Means these are magnetic field produced by the bar magnet. Now when there is a relative motion between these two, what happens? When both are at rest, suppose both are at rest, first observation, when both are at rest, then the magnetic flux means through this area, what is the lines of force passing through this area? That is called magnetic flux. When both are at rest, the magnetic flux linked with this coil area remain constant. That constant means the galvanometer shows no deflection. That means there is no current, no induced EMF, no induced current. Clear about that. Now when the bar magnet is moving towards the coil or away from the coil, what happens? The magnetic flux linked with the coil changes with respect to time when it is moving towards the coil or away from the coil. The magnetic field lines moving towards the coil, right, changes when it is moving towards the coil or away from the coil. It changes. The magnetic flux linked with the coil changes. Due to the change in magnetic flux with respect to time, that gives a induced EMF or induced current, which can be shown by the deflection of the galvanometer. Clear? So that is the Faraday's observation. The same thing is the magnetic direction. If you move the coil also toward the magnet or away from the magnet, the flux linked with the, so suppose these are the magnetic field lines. So this is a coil. When the coil is here, the field lines associated with this coil remain what? Less. When it moves toward the coil, more is the flux. When it goes away, less is the flux. So in that way, the magnetic flux linked with the coil changes. Then it induces EMF. One observation. So let me write one by one the observations is what. So the first observation, what can say that? What is the observation from this one? When the bar magnet and the coil are at rest, there is no current. When both are at rest, the galvanometer shows no deflection. When the bar magnet and the coil are at rest, the galvanometer shows no deflection or no current. No deflection or there is a no current. Clear? So that is the first observation about the. Second, when a bar magnet with its north pole facing towards the coil, right? So we can write this is a bar magnet with its north pole facing the coil. When the bar magnet with its north pole facing towards the coil, when the bar magnet with its north pole facing towards the coil moves towards the coil, the galvanometer shows deflection. The galvanometer shows deflection. That is the current induced in the coil. Current induced in the coil. Then the same case is when the bar magnet. You can write the third one also saying that when the bar magnet with its north pole facing toward the coil moves away from the coil, the galvanometer shows deflection in opposite direction. This is also true for the same. Okay. So same as for, I can write here, same for away from the coil and also the south pole facing the coil and also the south pole facing the coil. That is the second observation. So all this means that there is a relative motion between the coil and the bar magnet. The next one is that when the bar magnet facing the coil moves faster. The bar magnet facing the coil. So this is the bar magnet and this is the coil. The bar magnet facing the coil moves faster. So this is the way it can move towards the coil or away from coil. The galvanometer shows a deflection. Clear? Means there is a current. But if it is moving very faster, it is moving faster, then the galvanometer shows a deflection, but the deflection is large. Large deflection means the strength of the current is more. More is the current induced in the coil. So if the bar magnet move faster, then the current induced in the coil is larger, or the EMF induced in the coil is larger. That is another observation. Clear? So from that also what means, as long as when the bar magnet moving toward the coil, means magnetic flux linked with the coil changes. Magnetic flux linked with the coil changes. If the magnetic flux linked with the coil changes, means the change in magnetic flux is very fast. Means with respect to time, the flux linked with the coil changes very fast, larger. Then EMF induced is larger. The induced EMF is larger. So that will give you the more is the current, induced current. Clear? So this is the about the experiment, Faraday's experiment. Similarly, this experiment also there are so many other observations are there that instead of taking this bar magnet, if we take another coil, clear? So if you take another coil, that another observation you can say that. So this is the coil. This is one of the coil like this, and a galvanometer is connected. So this is the galvanometer connected. Now let us consider there is another coil is this. With this there is a cell is connected. So this cell gives current I, and this current flows through this coil. Without taking a bar magnet, there is a coil placed near this coil with a galvanometer. Clear? Now if the current in this coil flows and both are at rest, it shows no deflection. But when that coil means it is what? This is called as the primary coil. This is the secondary coil, generally called as primary coil, secondary coil. Where the cell is connected, that is primary, and this is the secondary. When this primary coil moves toward the coil or away from the coil, then also the current is induced towards or away. Means the current induced, that is in opposite direction. Galvanometer shows deflection. The galvanometer shows deflection. Instead of taking bar magnet also, when the coil moves toward the source connected coil and the galvanometer connected coil, the primary coil moves toward the secondary or moving away from the secondary. This induces a current or EMF. That is also true. That was also observed. Clear? So these are the observed facts about the Faraday's experiment. Then another is that instead of taking this bar magnet, and another thing, whenever they both are at rest, there is no EMF induced in the coil. Then next is that if the magnet is held stationary and the loop is moved toward the coil, toward the magnet or away from the magnet, it shows deflection. Then both are moving with same velocity or speed. When both are moving with same velocity, means what is the relative velocity between them? 0. When both are moving with the same velocity, moving towards or away, the relative velocity is 0. Then the galvanometer shows no deflection. Then the galvanometer shows no deflection. Why? The rate of change of magnetic flux is constant. The magnetic flux linked with this coil is constant. So rate of change of magnetic flux is 0. Why? Because both are moving with same speed or velocity. The relative velocity is 0. The magnetic flux linked with the coil remains constant. The derivative of a constant is a rate of change of flux is 0. So EMF induced is 0. So when both are at moving with same velocity or speed, relative velocity is 0, then the galvanometer shows no deflection. Next, the galvanometer shows no deflection if we rotate the bar magnet without changing its position, only at that same place if we rotate. Means with this axis, the bar magnet is there and this is the coil. If I rotate this with the same position, then also it will not show any current. No induced EMF, no induced current. Why? If you rotate this, the magnetic flux, what is from here, because of no change in the relative position or motion, there is no relative motion, only at the same place it is rotating, the magnetic flux linked with the coil does not change. So EMF is not induced. Right? Then this is the about the okay. So this is about the Faraday's experiment. Now from this Faraday's experiment, you can write this Faraday's experiment what I told. You can write this point by point or the note is provided. Okay. Then we will go to the Faraday's, by observing this Faraday's experiment or by the observations and conclusion from these experiments, Faraday put forth a law, or Faraday gave a law that is called Faraday's law of electromagnetic induction. That is called the Faraday's law of electromagnetic induction. Faraday gave a law that is called Faraday's law of electromagnetic induction. This is called Faraday's law of electromagnetic induction. So then it is also called the Faraday's laws of electromagnetic induction. Okay. So on the basis of observed facts, on the basis of the experiments or observed facts from the experiment, Faraday gave a law that is called the Faraday's law in electromagnetic induction. Okay. What that law? The first one, Faraday's first law of electromagnetic induction. And the first law, that is also called the Faraday's first law of electromagnetic induction. Whenever magnetic flux linked with a conductor or coil, whenever magnetic flux linked with a conductor or a coil, or loop, whenever magnetic flux linked with a conductor or coil changes, an EMF induced in it. An EMF induced in it. Clear? Because of the relative motion of the coil or bar magnet or another coil, current carrying coil changes, magnetic flux changes, and whenever the magnetic flux leaves the conductor or coil changes, an EMF is induced in it. And if it is a closed circuit, then the induced EMF gives you induced current. Clear? That is the case. Then this induced EMF lasts long. This induced EMF lasts long. So long as there is a relative motion between them. So long as there is a relative motion between them. Clear? This induced EMF lasts long so long as there is a relative motion between them. The induced current will be there so long as, lasts long, so long as there is a relative motion between them. This is the first part. So this is also known as the qualitative. It gives you the qualitative idea of induced EMF. Qualitative. The first law gives you qualitative idea about induced EMF. So this is also called as the qualitative law. Qualitative. So this is the qualitative law. It is qualitative law of Faraday in electromagnetic induction. Then we will go to the quantitative. It gives you the induced EMF. It says that there is a change in magnetic flux, then that will give you the induced EMF. Rate of change of magnetic flux is there, then it will give you induced EMF. Then how much is the induced EMF? That is the quantitative. How much is the induced EMF? Then comes your second law. Then comes the second law. That is what the second law states. The second law. Let me write the second law. Second law. What it states? The second law states that it says that the magnitude of the induced EMF is the magnitude of induced EMF. The magnitude of the it is not about direction part. Direction part we will discuss later. I told that the magnitude of induced EMF, the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux. Rate of change of magnetic flux is it directly proportional to the rate of change of magnetic flux linked with the conductor or the coil. Conductor we can say that is also a form of coil. Clear? So mathematically you can write this is what? Quantitative. So the magnitude of the induced EMF, is proportional to rate of change of magnetic flux. Rate. Magnetic flux is 5 d phi by dt. Okay. So this is equal to E is equal to d phi by dt. Okay. So we can write this is equal to, or we can say this I can also write. Right. So we can write this as d phi by dt. So we can write proportionality is that the magnitude is equal to k d phi by dt, where k is equal to 1, which is the constant of proportionality. Constant of proportionality. Externally the value of k is 1. That the constant of proportionality is 1. So what we got? E is equal to, simply k is equal to 1 means what? The second law gives you E is equal to what? d phi by dt. Simply E is equal to, I can write here. So let me get this thing. E is equal to simply what? E is equal to, magnitude of E is equal to d phi by dt. If the magnetic flux linked with a coil changes from phi 1 to phi 2 in time t1 to t2. If the magnetic flux linked with a coil changes from phi 1 to phi 2 in time t1 to t2. At t1 flux is phi 1, at t2 flux is phi 2. In time t1, t2 respectively, then EMF, magnitude of EMF, I will not put this magnitude sign, so you think that this is the magnitude. E is equal to what? Change in flux. How much is the flux change? Phi 2 minus phi 1. What is the time? From t2 to t1. So these are same as what? This is equal to, simply I can say d phi by dt. That is the magnitude of the flux. Clear? So this is the magnitude of the magnetic flux. If the coil has n number of turns, it is not one turn. If there are n number of turns, then what is the induced EMF? For each coil, this is the flux. For n turns, n into phi. The flux is how much? N into phi. So E is equal to n d phi by dt. N is a constant. So you can write n phi, or this is equal to E n d phi by E is equal to n d phi by dt. Clear? Then what is the induced current? What is the, if this is the induced EMF? If the coil is in a closed circuit, The induced EMF gives you current, induced current. So the induced current I can write from here also. The induced current. So you can write this is the Faraday's law. From here you can take different forms. Induced current. The induced current I is equal to, what is the induced current? The induced EMF divided by EMF by resistance gives you current. Resistance of the circuit. Resistance of the circuit. Then I is equal to, what is induced EMF? E. Induced EMF is E divided by R. So this is E divided by, if R is the resistance in the circuit, so I is equal to E by R. And remember, this is only the magnitude. Okay. So this gives you the induced current. Okay. Or you can write this is equal to, E is equal to what? D phi by dt, and this is multiplied R 1 by R. So d phi by R dt. This phi is the magnetic flux. Here phi is the magnetic flux. Clear? Then you can write this also in other form also. As you know, in other form we can write, as you know, the magnetic flux phi is equal to surface integral of magnetic field B dot ds. If you put here E is equal to magnitude of E is equal to d by dt, what is that flux? Surface integral of B dot ds. That can also be write d by dt of surface integral of B dot ds. This is the flux. You can write also like this. From the flux statement we can write in the case. So from here we can say that, so the induced EMF, it depends on the rate of change of magnetic flux. But the limitation of the second law is that here so far we have discussed about the only the magnitude of the induced EMF. It does not tell us about in what direction the current will flow or the induced current will flow. Means we can say that the limitation of this one is that does not give the polarity of induced EMF. It does not, the second law, it does not, the second law does not give the polarity of induced EMF. Whether the current flows in the coil in clockwise or anti-clockwise, the direction part is not given in the second. It gives only the magnitude only. Okay. So gives the polarity of induced EMF or direction. It does not give the polarity of induced EMF or direction. Polarity means that is the direction of the induced current or direction of induced current. Because the induced EMF gives you induced current, it does not give the direction of induced current. And the direction part or the polarity of induced EMF or the direction of current is given by Lenz's law that we will discuss. This induced current or this gives you what direction the polarity or in what direction the current flows or the induced EMF that we will discuss in your Lenz's law. Okay. So what we discussed here, what is electromagnetic induction? This is the introduction. Then what is first observed by Faraday and Henry. Then what is the Faraday's and Henry's experiment? What are the observations? From that observation, what is the conclusion? That conclusion is put forward by Faraday in a form of a law. That law is called Faraday's law of electromagnetic induction. And we state the two laws, first law and second law. First law is the qualitative, second is the quantitative. What is qualitative? When there is a magnetic flux linked with the coil changes, it induces an EMF. Second says the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux. That is the second law. Clear? So with that we go, and then we will the direction or the direction of current or the polarity of induced EMF is given by Lenz's law. Okay. So this next we will discuss about the Lenz's law. Clear? Okay.